Bismillah ar-Rahman ar-Rahim. Today we will discuss electrical safety. Before I begin, I want to remind you by what's called polarization in the pyroelectrical sensor that measures the temperature of the tympanic membrane or from the external auditor canal. It's based on as if the molecule, which is formed of different atoms, are divided on both sides. Each side has either a positive or a negative charge. You see, so this is what we call polarization. As if the molecule has two sides, each one has a different electrical charge. So whenever an incident rays of radiation passes by, this creates a potential, and this potential is utilized by the two slides of the capacitor, where this rays has been shifted to be transduced to an electrical signal, which can give me a hint about the temperature. So water is a polarized molecule. Why? Because you have one negative oxygen, and on the other side two hydrogen, which are positive. Oxygen or nitrogen, all these are non-polarized, but as long as there are two parts in the molecule where each of them possesses more or negative molecules, this we call it is a polarized molecule. See, so I'm utilizing this to gain the amount of temperature by the pyroelectrical system we mentioned before, to measure the temperature from the air. Electrical safety, of course, the problem of electric current can induce electric shock or can induce burns. How does the electricity created? As we said before, it is created by moving a current through a magnetic field. These movements can create current. This current is used to create electricity. So the main station forms around 11,000 volt, and then it goes to a substation, as we'll see later on. This substation, by transformer, shifts this amount of electricity to be 240 in England and or 110 in North America. So this electricity reaches the hospital by two wires, as will be seen now. The two wires is either live or neutral. The two wires reaches the socket, and the socket by the plug is being transferred to the electrical equipment. Of course, the substation is communicated, as we see, with the earth, and the socket also is communicated with the earth, and the floor of the stator also is communicated with the earth. Whenever I want to measure the amount of electricity that I may be affected, I consider first of all the resistance of the skin and the tissue is very minimal. It's around 100 of ohms. But the resistance of the floor and the footwear is much bigger than that. For instance, the potential which is the volt is around 240 volt, and the impedance, which is the resistance, but is correlated to the frequency, as we said before, is 240 also, but 240 mega ohm, so that we must multiply by 1,000 to get a proper figure corresponding to the volt. The final figure we multiply by 1,000 milliampere to get the figure in milliampere. So sometimes in the circumstances, if they are similar, the patient can, or the anesthetist may feel that 1 milliampere as tingling. It will not much affect him, not like if the impedance is much less than that. We will be seeing now if the impedance is around, as we said, there is defect in the footwear, or there is saline on the floor, or the protecting manner of the floor is not accomplished. So we will divide the 240 over only 10. 10, of course, 10 will multiply by 1,000 to get an ohm, and then finally we will get 24 milliampere. This is capable to cause spasm, and it will cause ventricular fibrillation. This is why as a protective element, whenever I give a question how to protect against electric caution, of course, the resistance of the floor must be from 75, which is less than, which is more than 10, as you can see. But the 75 is only kilo ohm, and then we never forget that the resistance of the skin and the tissue is only 10 kilo ohm, and the range reaches to 10 mega ohm. So this is the range you must memorize so that you can state it in the exam, how to guard against electric caution to make the earthing difficult to an extent which will lessen the effect of electrical caution. Of course, if the floor is full of saline is a good conductor for electricity, and it will help inducing the electric caution. Of course, if we have a cannula or needles in our skins, it will hasten also the electrical current. This is a figure showing the anesthetist touching a live wire, You see, this is how he may be electrically coated, as long as he's touching, and the electricity, as you can see dotted, it goes through his body from the arm to the leg, and then passes by the earth. The earth goes to the substation where the circle is completed, so that the patient or the anesthetist may have an attack of ventricular fibrillation. Of course, if the floor of the footwear has a minimal resistance. This is another figure showing how this guy can be electrically coated. As you see, there is a defect in the neutral wire, and then this guy is touching the floor, which is full of saline. And of course, as you said, the saline decreases the impedance, so that he can be electrically coated by the electrons passing by his body through the saline to the substation and goes back, creating an electric caution. Why? Because the impedance of the skin, as we said before, and the tissue is a few hundreds of 10 kilo ohm. And as we said, the range of the floor or the footwear must be from 75 kilo to 10 mega ohms. Of course, what helps also, we have needles, as we said before, and we have cannula, we have a wide surface area touching a large area. And of course, if the electrical current reaches the heart during the P wave, it's liable more to for electrical electric caution, causing ventricular fibrillation more easily. Of course, whenever the current is within the 50, 60 hertz, as we know in our country and in the rest of the countries, the incidence of ventricular fibrillation is more. But the electrosurgical equipment like the Lacermi, the frequency reaches kilohertz, so the incidence of ventricular fibrillation will be will not occur. Of course, how to guard against electric shock. Of course, this is the equipment standardization, as we can see, is made to fulfill the International Electronical Commission Standard 601 to fulfill the proper protection ways in such equipment. We can divide the equipments into three types. First, the class 1 equipment. Class 1 equipment, as will be seen in this figure, is an apparatus connected to the earth This apparatus has only one layer of insulator, and the electrical circuit within this box. In case we have what we call shortage, means that this electrical something happened inside, and this electrical equipment touched the outer case where I can touch. You see, so what happens to guard against such electrical quotient? Just I apply what we call fuses. As you see, 2 fuses on the neutral and the live, and we have additional fuse on the socket. You see, so whenever this communication or shortage occurs, heat, of course, as you know, electricity creates heat. This heat is capable to cut off this current by separating the fuse. So this is the ERCIT equipment, how they are utilized to guard against electrical quotient. The second thing in the equipment class of equipments, and I double the case. I have 2 layers, or I reinforce it and make it second. This is the second type as regarding the equipments for protection of against electrical quotient. The third thing is to use internally powered source as batteries. You see, so whenever I have a battery, I avoid the complication of electrical alternating current. But still, of course, if I yield a figure of, by dividing the potential on the resistance, suppose that the volt is only 12, the potential is 12 volt, and the resistance is supposed to half kilo ohm, so the figure will be can reach 24 milliampere, causing electrical quotient. So it does not guarantee against electric quotient, but it avoids the complications of the hazards of the alternating current. As you can see, that the problems of this patient, the patient is sleeping on the table, and his feet is touching the hot bulb apparatus or equipment, and then there's a fault. As you see, the wire is being cut. Whenever the current goes through the patient, it can be circulated through his feet, reaching this part and going to the ears and going to back to the substation. So this patient is liable to be electrically coated. Of course, as we know, the electrical blankets that are used to guard against loss of the radiant heat of the human being, the heat loss by radiation. Of course, any hot object releases this radiant, so it loses heat. So this electrical quotient, this electrical blanket can be a source of electrical quotient by mistake. You see, so you must put in your mind such situations. Of course, the current may go also through the ECG electrodes, causing problems. We have what we call inductive and capaciting coupling. These are a coupling of created through instruments. Most of instruments or monitors contain inductors and capacitors, as we say, inductor and capacitor. This both can induce what we call leakage current. This current, it's very minimal, but in some circumstances can induce also ventricular fibrillation in what we call microshock. Microshock is a minimal amount of electric current, around 150 microampere, not like the 24 milliampere that induces ventricular fibrillation from the hand to the feet. You see, so this occurs with intracardiac catheters, the thermometers being placed in the lower esophagus. They are near the heart, near the atrium. All these are source of electric current reaching the heart. You see. So what happens to this for this small current to induce a ventricular fibrillation? Of course, the most of this current supplied by equipment is around even less than 1 volt. We'll be seeing such what happens whenever I induce these capacitors and how can it cause microshock. This is another figure, first of all, that shows how the patient is being electrically coated by a minimal amount of current. As you can see, there is a defect in the wire. So the electrical current goes through the capacitor, as we said before, the microshock. This capacitor is touching a small area of the heart. That means that the current density is very high, not like a large current density is very slow. So small. So a minimal amount of currents up to 150 microampere is capable to induce ventricular fibrillation. As you can see, the current will pass through the patient, passing by the lamp source and go into the earth and completing the circuit where the patient can be electrically coated, though he received only 150 micro ampere. This is another source where the anesthetist is a source of earthing. As you can see, also there is a fault. The electricity is going through a capacitor to the heart, but instead of the patient touching the lamp, he is touching the anesthetist. The anesthetist is touching a monitor, and this monitor is earthed. So the circuit is completed through the anesthetist. Okay, why doesn't the anesthetist complain of anything? Because the current here is only 150 microampere, but it will induce ventricular fibrillation, but the anesthetist will not feel such change. This is the point why the anesthetist is not affected, why the patient can develop electric motion. As we said before, we have what we call leakage current. This is the current induced through the passage of current through inductors and capacitor within the monitors. Sometimes you feel it on top of the monitor where you feel some sort of electricity. This minimal current can, of course, as we said before, can induce microshock. So whenever electrical equipment comes to your department, you must check off. What's the meaning of that? We have electrical equipment used in open heart or cardiac surgery, and we have that used in non-cardiac surgery. Why we are concerned about that occurring in the cardiac surgery? Because most probably this type of surgery may introduce capacitors through the heart. So the leakage current in such instruments working in the heart, the floating, as we said, the floating. We didn't say before the floating was the meaning of floating apparatus. We will mention now. And I want to know. I want to tell you that the minimal amount of leakage current in such equipment must be at least not more than 50 microampere. On the other hand, the equipment, the monitors working in non-cardiac surgery, we have two types. We have B and B floating. We will tell you later on what's the meaning of floating. The leakage current maximum is 500 microampere. These are equipments that are useful in the operative theater where they cannot affect the patient. Isolating patient circuits or what we call floating circuits. This is circuits in which the electrical component of the apparatus is separated from the monitor that is attached to the patient. So you're making a breakdown through a transformer, you see. So whenever whenever anything happens, this electrical equipment is not going to be transferred to the patient. This is why we call it floating. You see, floating means that they are the electrical hazards is being separated from the patient, wherein as if anything happens in this electrical equipment, and what is not going to be reflected to the patient. This is what we call floating circuits. Of course, as we mentioned before, we have the three classes of equipments. we have how we protect by the footwear and the resistance of the floor. And the fifth thing is the floating circuits. And in addition, you must be acquainted about the instruments of the monitors being used in the operative theater, whether it's cardiac or non-cardiac. The pacemaker, of course, we have what we call external and internal. The external pacemaker is temporary, where we introduce the catheter through the pulmonary catheter and so forth to reach the heart, and there is a battery outside the patient. The permanent one is where we it needs a cardiac surgery. We apply the electrodes in either in the ventricle or in the atrium, whatever, and then the battery is also, as we see, implanted inside the human being. What is the problem of this diathermy of this pacemaker? Of course, most of pacemakers are called demand type. What's the meaning of demand type? They are giving the impulse as long as the heart does not work. If they sense that the heart is being begins to contract, it stops, gives the heart the upper hand to work. All the pacemakers didn't have this opportunity, so whenever anything happens, the heart can be any electromagnetic wave coming from outside. The electrodes will act as aerial, so they will think that as if the heart is contracting, so they used to stop. Whenever they stop, they cannot work again. The only way is to apply a magnet outside. This magnet makes this pacemaker acting as a constant time. It works giving a constant rate. So this is the way how to deal in whenever this non-demand type of pacemakers are subjected to this affected by the electromagnetic wave coming from machines, so that they may think that as if they are coming to the heart and stop working. But nowadays, demand types are capable to deal with such problem. Of course, the apparatus works at around 4 volt, and the duration of the impulse or the pacing is around 1 millisecond. Of course, the apparatus which works with the diathermy or may interfere with the diathermy is, of course, the microwaves, as we can see. These are equipment that may release electromagnetic waves, which deceives the pacemaker, so that the pacemaker will think that as if it is coming from the heart, so they stop. This apparatus must be taken care whenever I use anesthesia patient having a pacemaker. Instead of using the diathermy, of course, we can use, instead of the monopolar, we can use the dipolar. And whenever I use a monopolar, I must not exceed application more than 1 second. So this is the problem with the pacemaker whenever I anesthetize the patient with it. Alhamdulillah, well, I hope that I succeeded. I will improve myself as every time I say such words. Wassalamu alaikum wa rahmatullah wa barakatuh.